Hello friends, this is Devbrata Pramanik and you are watching my channel Physics Friends. Today we are going to discuss about the electrostatic potential of a uniformly charged sphere. Look at the figure. We have considered a uniformly charged sphere of radius capital R and having uniform volume charge density rho and total charge capital Q. First, we will find the potential at a outside point. To find the potential at a outside point, we have to bring a positive test charge from infinity to that point. To do this, the required work done would be the potential, and this potential would be minus integration over E dot dr, and the limit of integration is infinity to r is the distance from the center of the concerned point, and finally you get q by 4 pi epsilon naught r, as E outside this sphere is q by 4 pi epsilon naught r square. So the potential on the surface would be q by 4 pi epsilon naught capital R. We just have to replace this small r by the capital R. The toughest job is to find the potential at a inner point. Let we consider a inner point which is at a distance smaller from the center. To do this, we have to first find out the electric field at this point. What about this electric field? To find out this electric field, let we take a Gaussian spherical surface of radius smaller, and Gauss's law over this surface, applying Gauss's law over this surface, we get ER, that is electric field at R, into 4 pi r square is equal to charge enclosed by this closed surface by epsilon naught. Charge enclosed by this closed surface is equal to 4 by 3 pi r cube rho. So ultimately we get rho r by 3 epsilon naught. Now here we are going to find out the potential at this point. To the potential, to get this potential, we have to bring a positive test charge from infinity to that point. This work done, we can divide this work done into two parts. First, we bring their point from infinity to the surface. This portion gives us the potential of the surface, that is equal to q by 4 pi epsilon naught r, and in the second part we go we drive the charge from this surface to the field point. Thus the potential at a inner point, at an inner point, would be like this, where r less than capital R is equal to minus integration over E dot dr infinity to capital R. This portion gives the potential of this surface, then minus of capital R to small r E dot dr. A question arises, why we take minus? Actually, potential energy is nothing but work done against a force, so we take this minus. So if we take this electric field rho r by 3 epsilon naught, the electric field expression inside the sphere, uh, in this equation, then we get this type of expression, and integration over this term, look at the expression r dr, we get r square by 2. So putting the limit, we finally get this. But total charge q is equal to 4 by 3 by r cube rho. So if we replace this rho by capital Q, we finally achieve at this expression, q by 4 pi epsilon naught capital R into 3 by 2 minus r square by 2 capital R square. This is the potential expression at an inner point, that is small r is less than capital R. But q by 4 pi epsilon naught r, look at this expression, q by 4 pi epsilon naught r, this is the potential energy at the surface, we call it V capital R. So ultimately we get the potential energy at an inner point is equal to V capital R into 3 by 2 minus r square by 2 r square. If we take 3 by 2 outside the bracket, first bracket, the round bracket, then we get another expression. We get 3 by 2 q by 4 pi epsilon naught capital R into 1 minus r square by 3 r square. But here 3 by 2 q by 4 pi epsilon naught r, it is the potential at the center, because if we take r is equal to 0 here, we get here v0. So this expression must be this part must be the potential at the center v0. So another expression of Vr would be like this, V0 into 1 minus r square by 3 r capital R square. Now look at the these two expression. The term within the round bracket or first bracket, this implies a parabola. So within the if we draw the potential graph with distance, then the graph will take like this up to capital R. This is 3 by 2 Vr, this is potential at the surface at a distance capital R. This portion is parabolic within the sphere, and this portion is hyperbolic, that is it is proportional to 1 by r. We know that the potential outside the sphere is q by 4 pi epsilon naught smaller. So this must be it is proportional to 1 by r, so it is hyperbolic. So we get the potential inside the sphere parabolic and outside the sphere hyperbolic. Thanks.